This is the JBA Trust mini flume. It shows water in a simple channel. We're able to insert various different models of engineered structures, and we can see the effect of these structures on flooding, and we can see how good design and maintenance can have an effect on the river channel.
This Perspex flume channel has a gradient of 1 in 1,000. If you were to scale this up into the real world, the roughness would be similar to that of concrete. We have these scale models of typical engineered solutions which we might put into the river. We can put these into the flume and they show the effects that they might have on the flow upstream and downstream.
We have a large grey tank containing about 100 litres of water. In this tank there's a pump which pumps the water up into the flume channel and it drains back down by gravity.
This insert represents a typical broad-quested weir. Historically, these weirs were placed into the rivers for mill power, and nowadays we can use them for hydropower schemes, but they represent barriers in typical rivers these days. Currently, the channel is showing unobstructed flow. The current water level is 2 centimetres. What we're going to do is add the weir, and we'll show you how this affects the flow. As you can see, the water levels have significantly risen upstream to 9 centimetres due to the weir obstruction. Downstream has fallen to 1.2. By adding the duck into the river, we can see how the velocities have changed in the channel, going from slow upstream to much faster downstream. So this represents an obstruction to the flow downstream of a weir. In this situation, the water levels can start to back up towards the weir itself. This causes water safety issues for anyone passing over the weir, and in particular in our situation a kayak. As the kayak comes down, goes over the weir, it gets stuck in what we call a stopper, and as you can see the kayak is completely stuck there and the person in there will not be having a great time. This insert represents a bridge pier. Bridges can be used for footbridges, roads, railways, anything to get yourself across from one side of the river to the other. Bridges can be either designed straight on, like this, supporting the bridge on top, or they can be at an angle to the river flow. So in normal unobstructed flows, the water level is currently 2 centimetres, upstream and downstream. As I put the straight bridge pier in, you can see the water level increases up to 4.5 centimetres upstream, and downstream it decreases to 1.5. You can also see the scour effect at the bottom of the bridge, and by using our duck we can see how the flow slows down upstream, and as it goes past the bridge it goes faster downstream. So if we change from a straight pier to a skewed angled pier, we'll see what happens to the water levels. Upstream it increases further from 4.5 up to 6 centimetres, and downstream it goes down to 1 centimetre. You can also see how the scour effect changes through both sides of the bridge pier, increasing that scour. This time if I add the duck into the river, we can see same effect, slower upstream and faster downstream.
This is our model of a culvert. It's an arched culvert with a straight section throughout it. Culverts are used for various different reasons. In built-up areas, they can transport watercourses underneath the built-up areas, whether it's houses or buildings. They can also be used to transport watercourses underneath infrastructure, for example, railways and roads. First of all, we're going to check the velocity. We can see it's a nice constant velocity. And the height of the water at the moment is 2 centimetres. So now we're going to insert our culvert unit into the flume. You'll see that the water level is rising and it is now measuring 6.5 centimetres. We're now going to see the effect on velocity by putting the duck into the water. It's fairly slow, and as it gets to the channel, speeds up. One way to reduce upstream water levels to culverts is to introduce a tapered entry. So for this purpose, we're going to use these wing walls. The current water level is 6.5. So let's put these into the flume. The water level now is 6 centimetres. So it's reduced the water level and the water is flowing more freely through to the entrance of the culvert. By putting the duck into the channel, we can see the effect of the wing walls and the tapered flow. Culverts are often classed as hazardous environments and can be confined spaces. As a result, culvert screens are often installed to help prevent safety issues. However, the installation of these screens can create other issues, including increased water levels. We have 3 different culvert screens: vertical screen, angled screen and stepped screen, and these will show various different effects on the water levels and velocity. So this is our vertical screen, and we'll add it to the channel. Vertical screens create a real risk to safety. For example, if a person gets washed down a river and pinned against a screen, there's no way of getting out easily. These kind of screens also make screen clearance and debris clearance very difficult because it's very tricky pulling up the debris off the screen, particularly when there's a high pressure behind it. For the purposes of our demonstration, we're going to use this scouring pad as our piece of debris. By adding it to the channel, we can see the effect of debris on a screen. And the water level has now risen to 13 centimetres. Here is our angled screen. So we'll add it to the water to see what effect it has. So the water level has risen to 6.8 centimetres. By adding debris to the screen, it's risen slightly to 8 centimetres. By introducing the duck, we can see there's slightly less risk of getting pinned. The water is flowing more freely through the flume. The third type of screen we will look at is a stepped screen. So this has more surface area than the previous 2 screens. By adding this to the water level is now 6.6 centimetres. And again, by adding our debris, we can see that the water level has risen slightly, but not quite as much as the others. It's now 7.6 centimetres. Taking the debris out, we'll just show how the duck moves against the screen. Slightly less risk of getting pinned. There's now not enough pressure to hold it against the screen. This type of screen is also more easily cleaned by being able to scrape the debris off at an angle. This structure is a vortex control device. We use these to regulate the flow out of ponds and reservoirs. We'll now insert it. So these devices keep the flow rate constant even if the upstream water level increases. They require no power and very little operator intervention.